I am Dan Harkins, and as she mentioned, I work in the office of the CTO, and I want to talk to you about some of the protocols that I created that have now become known as WPA3 and Advanced Open. So the security that we talk about in wireless today is pretty old. It's like 15 years old, and I don't remember if any of you people recognize what this is. This was the state of the art back when Wi-Fi security that we're using today was invented. PCMCA card doing 11B, 56 megabits. Woohoo! That was the state of the art. So we've had a lot of advances in networking, in mobility. Now we're doing 11AC, AX. We're getting gigabit speeds. We no longer have PCMCA slots in our laptops anymore. But security never got evolved. So that's what WPA3 is going to do. Back in the day, people were worried that access points didn't have enough computing heft to do a good cryptographic key exchange protocol. So we ended up with this WPA2 PSK mode, which is fundamentally flawed. And everybody basically knew it at the time, but that was, they thought, the best we could do. And then the alternative was, if you wanted robust crypto, you could offload that processing onto a radius server and do 82.1x and eat, which is really complicated. So the options we gave people were, well, you've got broken PSK, or this incredibly complicated and very difficult to configure and hard to scale. And that's what we gave people to build networks with. And there's that old saying, like, if you have a hammer, everything looks like a nail. Well, if all you have is a hammer, you're not going to be able to build anything very good, right? And so all we gave people as tools was PSK and .1x. And as a result, people tried to build the best networks they could, but again, back in 2004, we didn't realize that Wi-Fi would be everywhere like it is today. It's ubiquitous. You go into a coffee shop, and you just expect it to be there, right? So the tools that we have are not suitable for the networks that people are building today. That's where WPA3 and Enhanced Open are going to come in. So we're going to try and address some of these flaws and address some of the use cases that WPA2 just does not serve. So from a top-level view, open networks are going to be replaced by Enhanced Open, by OWE, Opportunistic Wireless Encryption. So that's just basically going to take an unencrypted network and encrypt everything. Still no authentication, but it's encryption. We're going to fix the PSK flaw, which is allows people to recover passwords, and replace that with something called SAE, Simultaneous Authentication of Equals. There's an optional upgrade to WPA3 Enterprise Security, which is something called Suite B, or the Commercial National Security Algorithm. And this basically establishes a level set for security for accessing an enterprise network, and takes away a lot of the options for misconfiguring WPA3 Enterprise or WPA2 Enterprise out of the loop. Also, there's some changes to certification testing. One of the things we realized when WPA2 certification came out, it wasn't very good, and a lot of clients came through that did things that they probably shouldn't have done, and they still got certified anyway. So we're closing off some of those testing bugaboos. So I want to dive down into each one of these a little bit. So again, for Enhanced Open, it's based on this RFC that I wrote, RFC 8110, Opportunistic Wireless Encryption, and it basically overlays an unauthenticated Diffie-Hellman on top of association request response, the typical .11 association request response. So at the end of this OWE exchange, the station and access point have a pairwise master key. And there's only going to be two entities in the entire world that would know what this master key is, and that is the client and the AP that engaged in this exchange. So that PMK then is used as a four-way handshake, and everyone gets traffic encryption keys, and nobody else knows what they are. So, if you're paying attention, you're going to say, well, Dan, you said it's an unauthenticated Diffie-Hellman. That's not secure, right? Well, yes, unauthenticated Diffie-Hellmans are not secure because the station doesn't know what network he's really connecting to, and the access point doesn't really know which client is connecting to him. But in spite of that, it's still more secure than the way people have been using WPA2 PSK. Like if you go into a coffee shop or a bar and somebody's written the password on a chalkboard, that's extremely easy to recover. And this is actually more secure than that. One of the nice things is it's completely transparent to users and admins. So when people come up to a WPA or to an OWE network, it's going to look just like open. They're just going to click on it, they're going to get connected, and they just think it's just like an open network. But underneath the covers, we're actually doing the Diffie-Hellman exchange, generating a secure key, and doing the four-way handshake. And again, this addresses some of those use cases that WPA2 did not cover very well. There's a thing called transition mode so that we can seamlessly go from open networks to OWE networks without having a big flag day. And what happens is when people are now configure an open network, there's going to be a cloned hidden BSS next to it. And this one is going to it's going to hide the SSID, but that's going to be where OWE is done. So when a station starts scanning, he's going to see this open network. And if he's an OWE client, he'll notice that in the beacons, there's a new information element that says, hey, if you know OWE, go over to this hidden BSS, do OWE there. And so old legacy clients that don't know what OWE is, they're not going to recognize this information element, they'll just throw it away, they'll connect open. But all the OWE clients will go to this other hidden BSS, do OWE, and basically generate a PMK, as I mentioned, and then do the four-way handshake. So the next thing to dive into here is,
yes. I was going to ask you, I asked you earlier about this, and you said you would tell us the story of why it's optional?
Yes. Quickly. It was optional because nobody pays attention to security until it's thrown in their face. And a lot of people, or a small core of companies, worked on OWE as part of WPA3 and got it to the point where it's going to be ready. And I think some other companies looked at it and said, what is this WPA3 stuff? Because the Wi-Fi Alliance did an announcement in January saying OWE is included in WPA3, right?
Yep. Which is a brilliant idea.
So all of these companies that had not been paying attention to security went, what the hell is this, right? So then all of a sudden, we got a whole bunch of more companies interested in WPA3, and they said, too much, we don't want to do this, rip it out. So we were basically held hostage to the, if you want to get the program out, we got to, take it out and make it optional and then do them both at the same time. So it was a hostage situation. It wasn't comfortable, and I'm very upset about it.
Oh, me too, but thanks for sharing.
Okay. So, SAE. So the problem with PSK mode is it's susceptible to offline dictionary attack. And so what happens there is somebody can just passively observe an exchange going by, and they can take that information that they observed, go offline and run through all possible passwords until they get the right one, and they're able to decrypt the handshake. People have created FPGAs, arrays of FPGAs that are specifically programmed to do this attack. So they can actually do hundreds of thousands of PSKs checks per second. So this protocol really is 100% broken. There's really no secure PSK you can use. You might think you've got this big, strong PSK. You don't. So the way to fix this is use SAE, which is a password-based authentication protocol based upon this Dragonfly key exchange, another RFC that I wrote, 7664. And this is resistant to dictionary attack as well as passive attacks and active attacks. If you guys are comfortable doing PCAPs and packet captures and looking at packets, you probably noticed that most of the interesting stuff happens post-association. But with SAE, it actually does the handshaking with authentication frames, 802.11 authentication frames, which is before association. So if you're looking for SAE, look in authentication frames. Similar to OWE and Open, the nice thing about SAE is the provisioning is identical to PSK mode. So the workflow for users, they're comfortable to seeing, they see an SSID, there's a lock, they click on it, and it says, enter your password. They enter the password, and they go, okay, and now they're on the network. So that same workflow is the same with SAE. There's no change to the user experience or their expectations. But again, underneath the covers, we're giving them much increased security with no added complexity. So you might say, well, how does this work? How come PSK mode is susceptible to cracking and SAE is not? So what SAE does is instead of taking the password and using that as a credential in the authentication protocol, what it does is it uses the password to index into an elliptic curve and get a secret point on the curve. That point is then used in a cryptographic exchange, which is Dragonfly. And the result is that if you start with the same generator, which this indexes into an elliptic curve to create a generator, if both sides know the same generator, they'll generate the same shared secret. If they have different generators, they'll generate a different shared secret. So, and since the password indexes to create the generator, if you have the same password, you'll create the same secret. If you've got a different password, you just create a different secret. And that's all you know, basically. So the nice thing about this then is passively observing an SAE exchange tells you nothing. it's secure under what's called the computational Diffie-Hellman assumption. So even if an attacker knows the password and he watches SAE go by, he's not going to know what the PMK is, and therefore he won't know what the traffic encryption keys are. The other nice thing about this is that the only way to actually attack SAE is to do repeated active attacks. What is called the adversarial advantage grows from interaction and not computation. So with PSK mode, it grows from computation. You watch one exchange go by, then you start computing, and you crack it. But with SAE, you can't do that. So you just get one bite at the apple each time. So what this means is that we can use what people constantly refer to as weak PSKs, which are kind of short. People say with WPA2 PSK, it's got to be like 20 characters, camel case with special characters and numbers and all that crap in there. But with SAE, you can use the passwords that are much more easy to remember, easy to enter, easy to manage. And that's because the only way to crack it is through, again, repeated active attacks. So the probability of guessing the password is basically 1 over the number of possible passwords. Now, for example, if the password is a number between 1 and 1 million, that would be really stupid with WPA2 PSK. You'd crack that in a matter of seconds. But with SAE, it's going to take about 500,000 active attacks to even get a probability of 0.5 success. So it's very easy to detect active attacks. So again, this is much more secure. The other enhancement to WPA3, this is optional. It's Suite B, or it's now called cryptographic national security algorithm, commercial national security algorithm. So one of the problems with WPA2 Enterprise is that there are so many options to EAP and TLS authentication, and it's very difficult to debug. So what people did is, in the Radius server, they just make it accept almost any offer that's made to it. It'll say, yeah, sure, we'll negotiate that TLS for you. So what happens is you can get some clients that get they negotiate a nice, strong cipher suite. You'll get other ones that are doing maybe TLS 1.0, they're doing SHA-1, or they're doing Diffie-Hellman with some really small group that's insecure. So you've got this mix of, strongly authenticated clients, weakly authenticated clients. It's kind of a mess. So with Suite B, what they do is there's a constant level of security. Everybody who connects has to use one of these 3 TLS cipher suites. So what you basically notice, the common denominator here is AES GCM mode with 256-bit key, SHA-384, and the 384-bit elliptic curve. Or you can do an RSA key that's 3K long. The way this gets handled in EAP is that the authenticator now includes a new Radius attribute in the authenticate request that it sends to the Radius server. And that Radius attribute says what the AKM is that the client negotiated. So when the Radius server notices that the AKM is Suite B, he's going to say, OK, only negotiate one of these 3. So that ensures that when the client gets authenticated, he's gone through Suite B compliant 802.1x and EAP. Once it's done, again, since it's Suite B, they're going to use SHA-384 for the KDF when you do the 4-way handshake. And then again, you get 256-bit encryption. So the last one I was telling you is that there were some testing bugaboos that we discovered kind of late. One of them was that certificate chain testing for clients was not done very well. So there were situations where you'd have a chain of certs and maybe an intermediate cert somewhere was expired. So the client should have rejected authentication because going up the chain, you go, OK, no good, reject authentication. They didn't do that. They basically checked the first one and the last one and said, OK, run with it. So we've fixed that by including some additional tests for WPA3 Enterprise certification to ensure the clients properly handle certificate chains. And we've also made management frame protection mandatory. 11i, which is what WPA2 was based on, came out in, again, I was saying 2004. That only concerned data frame protection. 11w, which came out in about 2009, did management frame protection, but it was always optional. And being optional, very few people implemented it. So with WPA3, we're making management frame protection mandatory. So the high-level takeaway for this, then, is with Enhanced Open and WPA3, is we're going to get encryption everywhere. Coffee shops, captive portal, things like that. And we're going to close down known attack vectors. It's not possible to do a dictionary attack against a pre-shared key anymore. You can't passively observe an exchange in a coffee shop And of course, since the attacker knows the password, everybody knows the password, it's written on the chalkboard, right? So the attacker's not going to be able to attack that and determine what the traffic encryption keys are and attack the clients. And again, mandatory management frame protection eliminates the possibility of doing a DAuth attack, which is what a lot of these attacks require. They start off with a DAuth attack. Again, Suite B CNSA ciphers, 256-bit. That's a new option. And the other thing I want you to take away is that we've increased the security without changing the complexity. Usually people think that these things go hand in hand. If you want to get more security, it has to be more complex. And that's a kind of a false dichotomy. With OWE and with WPA3, we've increased the security, we haven't increased the complexity. You guys notice the visitor network? Mm-hmm. It's an OWE network. Did you notice that?
Yeah.
Okay. We're going to do a demo doing OWE on.
Yeah. Good morning, folks. My name is Mac. I am with Technical Marketing, and I'll be, with the time we have, I'm ready to do OWE and SAE, but I'll start with OWE first. So I'll be with Ubuntu client here that's OWE capable. I'm going to hit a specific AP running on channel 112E. So if somebody want to take a packet capture as well, you're welcome. So from this end here, I will start the packet capture on the Mac OS.
How do we switch it to this screen?
So I'll start the packet capture from my end here. Yeah, so I started the capture on one laptop, and I'm moving to the client now. I'm going to run a script to quickly go through the OWE association and connection.
Drum roll, please.
All right, so here we see on the top that we are associated to that hidden SSID now, and which has in the middle Aruba Visitor, and down here the adapter we got an IP address, so I'm going to ping, and I'm connected to the internet. So I'll stop the capture here. And I'll move back to, so here I'm showing the two beacons there, the one that is in the clear.
Yeah, remember I said that with transition mode, there's two BSSs. One is hidden, and that's what it's called, it shows up as wildcard. And Aruba Visitor is the one that everyone is seeing.
Right.
So if you notice here's a new information element that's added, transition mode. This gives the BSS and the SSID of the hidden network that it's supposed to connect to.
And the hidden SSID is, here we have the RSN element, right? Mm-hmm. And we have also the OWE transition mode that points to the Aruba Visitor. So that's as far as the beacons. If we go now to the client itself, so we go through probe requests, authentication. Again, this is open authentication. There is nothing special here. Then we go into the association request, and this is where we are going to see the RSN.
And there should be a Diffie-Hellman element down there somewhere, right?
Yes. If I scroll down, we see the extended tag.
There we go.
OWE Diffie-Hellman.
And here's the Diffie-Hellman public key.
Right. So now we went through the association. Then we go from here to the key exchange. As we see, the four-way
Same old
key
four-way
exchange.
handshake that everyone's accustomed to.
Right. Message 1, 2, 3, 4, and from there, everything from there is encrypted. Okay.
We got
So
time for a SAE demo too? Yeah, 3 minutes? We can
yeah,
do it.
we'll go with that. Let me start now. I'll reset the client here, and then I'll start capture another capture. Yes, it is on the same channel. Okay. So I'm clear here. And so I'll start the capture again. And we have the capture going.
Can we switch over on the screen for the client?
Yeah.
So this is released software too. Aruba got certified for WPA3 and Enhanced Open. You can get this stuff running on your controller if you want. Okay, and there we are. Aruba Visitor SAE is the network. And can we find the authentication frames in there?
Let me see if I am running the. So here's where the authentication comes into play.
Right,
Dan,
so here's this is the SAE exchange. There's a scalar and an element that capacity in both of these. That's client to AP to client, and then they confirm that they have the same secret.
Then we have the association request here.
Which is just going to be regular old in the clear. There's no Diffie element there. They've already generated the PMK with this final frame here. And then they're going to do the four-way handshake.
Yep.
So, there you have it. Yes.
In general, why is this worth the cycles to do this? I understand WP3A is great, but this really feels like sitting in like a French war room in 1935, hearing about an Maginot Line upgrade, right? Like the attackers aren't attacking that; they're going to the endpoint. Like, isn't investing in TLS 1.3 or something way more important than pushing to WPA3?
If everything was the web and everything was then TLS 1.3 would be good. But we still need security at layers. We still need, we wouldn't get rid of IPsec because we have TLS. We're not going to get rid of Wi-Fi security because we have IPsec. We want all of the layers to be secured. And the fact of the matter is that it wasn't secured. WPA2 was flawed.
I know, but shouldn't companies be spending more time on client isolation, knowing that you're not going to be able to get everybody to WPA3 for 15 years, like your slide said?
Well, it was 15 years from 2 to 3, but it wasn't 15 years to get everybody on WPA2. We got
How long
everybody
do you
on
think
WPA2.
that window is?
A couple of years. WPA3 is going to be mandatory to get certified for AX. So everybody who has an AX client is going to have to be WPA3 certified.
But Google is still shipping all their IoT devices on 2.4, right?
Yes. Have you asked Google when they're going to do WPA3?
When it's free, I'm guessing.
It is free. Actually, if you look at Android, WPA3 and SAE is in Android already.
Yeah.
The problem is it's in the supplicant. It's not in the. They need some Java glue code that between the scanning and the UI to actually get the supplicant to do the right thing. Yeah. But the code is in there. They just need to write some glue to get it exposed to the user. So it's not going to be 15 years. It's going to be 2.
Is that going to be the same for OWE too? Like that's not going to require devices to be upgraded?
No, all of this stuff, except for part of Suite B, is all a software upgrade. OWE is a software upgrade. SAE is a software upgrade. The only thing that requires a hardware upgrade is probably 256-bit GCM, and that's because most of the data encryption happens in the radio chipset itself, and the radio chipsets basically have never done 256-bit encryption traditionally. But that's only for Suite B, right? So all this other stuff is just a software upgrade.
So Aruba will have WPA3 on all of their stuff in 2 years?
If we want to get certified, yeah.
Dan, are these scripts that you guys are running available? Are you either available for us or on GitHub or somewhere? For anyone who's following along at home kind of thing.
That's a decision made by somebody at a higher pay grade than I. I'll pass on that one. But we'll get you an answer.
That would be great. Thank you.